In this session, we will continue with the student presentations. Our first group of presentations will be from the Maritime Division students. Maritime Division provides technologies and scientific and technical expertise to deliver the capability edge to the warfighter and enhance the operational performance and survivability of defence platforms in the maritime domain. Maritime Division applies a range of technologies and undertakes analysis of the effects of their integration on the overall effectiveness of maritime systems. And we have David Kershaw, the Chief of Maritime Division, with us today as well. Please welcome our first presenter, Samuel Barnden.
Hi, I'm Sam. I'm working in the hydroacoustics group at DST, and I'm a student of the University of Melbourne. So the hydroacoustics group, among other things, is made up of mainly computational modelling roles, experimental studies, and dynamics and control. So how that works is the computational guys will make a model, experimental guys will test that, and the dynamics and control can use that data to figure out the dynamics of systems. So my project is the multi-hole pressure probe. It's to be used in cavitation tunnels, so it's like a water wind tunnel. It's a very small diameter probe, about 1 millimetre, 1.25 diameter. It measures velocity in 3 dimensions, which you get from the pressure readings, and it has a super high resolution and a high frequency data. That's important because we can get more information about the models that we're testing to be able to validate them more accurately. So the achievements that I've done to date, I've conducted a literature review, an integrated data acquisition program for the probe, a calibration algorithm, and I've tested the calibration in an on-site laboratory. So this is an image of the little on-site test tank that we've got. The image on the right, your left of the screen is the tank as a whole. So it's got a small pump at the bottom which shoots water through, and the pressure probe, as you can see in the close-up image, is in between the flow. Going a bit too fast, let's talk about it a bit more. So yeah, this probe is really small. It's got 5 holes which are about 0.25 mil wide. So the probe is going to be yawed and pitched in the flow. And using that data, I can analyze it in MATLAB to generate a calibration algorithm, and then this probe will then be sent down to the tank to be able to test and get the velocities from the flow. So where to next for the program, for the project? We'll do more testing in the tank. The probe's currently still in its testing phase and getting the data for that. We need to quantify the uncertainties and sensitivities, calibrate the probe obviously properly and accurately down at the Australian Maritime College cavitation tunnel, and then it's ready to be used to be put behind models of submarines, for example, to test the computational models and validate that. So, thanks.
Thank you, Samuel. Please welcome Bryce Clark.
Australia spends around $200 million a year on ocean surveys. These can be done in boats like the one you see here, with multi-beam echo sounders attached to the bottom. As the vessel moves, pings of sound are emitted from the device. The time taken for the signal to return to the surface is used to determine the depth of the ocean. Several thousands of pings can be combined with accurate vessel motion and GPS data to create a legal map of the sea floor. These maps are used to safely navigate waterways on all kinds of vessels. But sometimes there are false depth readings, like the ones you can see here that are caused by fish. If we look at a larger section of the sea floor, we can see that these spurious points are not uncommon. Sound waves can be influenced by anything in the water, from bubbles to debris or sea life. These don't just occur above the surface, but also below. Due to these false depth readings, our map is no longer accurate. But when we're spending all of this money, we can't afford to be creating misleading maps. Traditionally, this would have been a human data cleaning process, taking hours up to days of repetitive and mind-numbing work. My chosen method uses DB scan and takes a matter of minutes. We start with a point and only include that point in a cluster if it has a set number of neighbours within a defined radius. We then move to the next point and repeat the process. When there are no points left, we start a new cluster. The process continues until all the points that can be added to a cluster have been exhausted. There's one very important thing to notice here, and that is that not all points have been added to a cluster. These are the outliers and represent the spurious points that we saw on the previous slides. When this method is applied to several pings of multi-beam data, it looks something like this, where the red crosses are points that don't belong to a cluster. By eliminating these points on all pings in a survey, we get a much cleaner surface. This greatly increases the accuracy of the map, both above and below the surface. Here's a quick comparison between my method and two other point cleaning methods that are available. You can see that both methods have missed points either above or below the surface and have also reduced the resolution of the map by removing points on the true surface. You might have also noticed that my method segments the seafloor. This opens up the possibility of training a classification network that can determine the surface type or find things like shipwrecks. Currently, I'm working on more complex machine learning methods like neural networks and autoencoders that won't require knowledge of the data. You can see I've had some success with the autoencoder method. I'm going to leave you now to admire this section of an artificial reef that has been cleaned with my algorithm.
Thank you, Bryce. Please welcome Vincent He.
Hi everyone, my name is Vincent. I'm an undergraduate student at Monash University, and I've had the privilege this summer to work with the Maritime Division, or more specifically, the Acoustic Material Systems Group. A major component of the Maritime Division is in its acoustic signature management. There are many technologies and methods to accomplish this, which leads to my project, where we investigate the underlying physics and capabilities of emerging technology which manipulates sound using acoustic metasurfaces. Well, that's a mouthful to say, isn't it? Let me break this down for you. A metasurface is a subset of a larger category of materials called metamaterials, which are materials which have non-natural material properties. Let's break down more. Simply, they are materials which seem to break the classical laws of nature. Let me give you an example. So this is a metasurface that we've been investigating in the group, and the amazing thing that it can do is that it can take a perpendicular incoming sound wave and reflect it off at a different angle, which is classically unfeasible. What's even more impressive is that you can tailor the depths of these grooves to reflect the wave at any angle you want. That's pretty cool. But this is not a wonder material, sadly. This only works for a few frequency bands, but the interesting thing is that if we do place these tailored grooves in a certain configuration, one can create a one-way acoustic open tunnel, and it behaves as it sounds. So I've included some helpful simulations to visualize this phenomena. And it may look really cluttered, but the more intense the sound, the more intense the color, you can think of it as the more intense the sound. And so to the top right, you can see that the sound is quite attenuated as it propagates through the tunnel, whereas on the bottom right, the tunnel has been flipped around, and you can see that most of the sound is actually passing through. I've also included in the bottom left a metasurfaceless tunnel for you to compare against. For reference, these tunnels are about 300 millimeters in length at the moment, displayed on the screen. And you can tailor the grooves, depths, and their shape to allow or reject certain frequencies. My role within the investigation has been in building 2D and 3D computational models to characterize the behavior. I've also been conducting physical experimentation on the physical model you see on your left. I've also been looking for different configurations that we can build in the future. And what I seek to do within the last few weeks of the project is to validate this computational model. And once validated, it will be integral in explaining, designing, and implementing this technology. Thank you.
Thank you, Vincent. Please welcome Anna Lykke.
The ocean has a weather pattern that works very similarly to the Earth's atmosphere. This can cause temperature variations in the ocean, so polar regions tend to be quite cold, while equatorial regions tend to be quite warm. Now, sonar systems work by propagating sound waves through the ocean. These sound waves don't travel in straight lines, they tend to bend, and how much they bend depends on the temperature of the ocean. This can lead to regions in the ocean where there is no sound. These are called shadow zones, and these make perfect hiding spots for submarines because a sonar system has no way of being able to detect them. Changes in the temperature can alter the locations of these shadow zones. So what we aim to do with our research is to look for regions around the globe where we can get the best sonar performance and where these shadow zones are most likely to occur. So the temperature changes can cause changes in sound speed with depth, and this can be shown on the middle figure, which is a sound speed profile. There are two important features of these profiles that are important to sonar performance. So the first one we looked at was a surface duct, which traps sound energy at the surface and forces it to propagate long distances. The depth of this duct determines how much energy will be trapped, so a deeper duct will trap more energy than a shallow duct. The second feature we looked at was a below duct gradient, which is where all the energy goes that is not trapped within this duct. So the angles at which these sound waves bend can determine whether they will be trapped in the duct or be in the below duct gradient. So through our research, we also noticed the existence of double ducts. So these work the exact same way as a surface duct, but they occur much further down in the ocean. The two propagation loss models that are shown on the right show how much sound energy is trapped within these ducts. So the red regions indicate lots of energy trapped, which means we have a high chance of detecting something. And the blue regions means we have very little or no energy trapped, and we have a low chance of detection. And this is where our shadow zones tend to occur. So what we've learnt in our research is that deep surface ducts tend to occur in winter and polar regions, while shallow surface ducts tend to occur in summer and equatorial regions. If we are in the northern hemisphere, double ducts are most likely in the Atlantic, and if we are in the southern hemisphere, they are most common in the Pacific. So future studies could go into more detail on these sound speed profiles at these seasons, locations, and depths. This information is very beneficial for Navy to know, as it allows them to find the seasons, regions, and depths where shadow zones exist, which can help their ships avoid detection, and where the best locations are for submarine detection. Thank you very much.
Thank you, Anna. Please welcome Patrick McNamara.
Submarines are complicated and stealthy vessels designed to detect and classify threats in the ocean whilst remaining as silent as possible. They do this by listening to sounds passively underwater generated by other objects in the ocean, such as the propeller noises from enemy ships or even the biological sounds of whales and schools of fish. When a submarine receives data, it's receiving three-dimensional information: the bearing that the noise is coming from, the frequency spectrum, and the time. These are shown to sonar operators on what is known as a sonar display. Historically, these displays have been quite limited in terms of the breadth of information that can be shown, but recent advancements in processing power have allowed us to experiment with more dynamic kinds of displays. Here's part of a display that I designed over the course of my internship. So this first plot we have here is a bearing time plot, and the second one is a frequency time plot. They're both examples of what we call waterfall displays, because we have the most recent data sitting at the top, and it slowly trickles down as fresh data comes in to replace it. Now, when I was designing this display, I was considering adding a third plot, which is called a polar frequency bearing plot. This has bearing represented angularly and frequency represented radially. The problem with this type of plot is that it's updated continuously with time, and so it's got no way of representing the history of the plot at a glance, like the other two plots which have a time axis. So I discarded it for the time being and just moved on to other issues. So I started thinking about panning and zooming on the plots that I had, and the problem is when you start zooming in, like the bearing time history plot, for example, and you're zoomed in on between 50 and 100 degrees, and a warship starts making noise at 110 degrees, you're not going to see that until you zoom out a little bit further and can actually see the signal. So to get around this, I kind of stole the coordinate system from the polar plot that I was showing you earlier, and I created this tool here. This is just in MS Paint. It shows the visible bearing region here and the current bearing as a little indicator there. And then I also did the same for the frequency time plot. So frequency is represented radially here, and the searchlight area that you can see has been constricted in the radial direction. That's that yellow band that you're seeing there. So you're actually seeing the visible bearing region and the visible frequency band in one tool. And then I decided to overlay that over the top of the polar plot that I had earlier, and it kind of gives you an indication of where new data is that could be investigated. You can see some kind of structure in the data that I've circled here. So that might give you an indication that, hey, I should pan my bearing over so that I can see this new data that's happening. And yeah, that's the final display there. And yeah, by experimenting with different types of visualization and control mechanisms, we can improve the efficiency of the sonar operator's role and increase the overall efficiency of submarines in general. Thank you.
Thank you, Patrick. Please welcome Madison Simmonds.
Hi everyone, today I'll be telling you about the Michelson interferometer and how it relates to DST's optical fibre sonar array. So to begin with, a Michelson interferometer is an incredibly sensitive optical device that is used to make really precise measurements. So the way that it works is that a light signal is inputted into the instrument, it's then split into two, and the two signals are sent down the arms of the interferometer. At the end of each arm is a mirror which reflects the light back towards the beam splitter, where it's recombined and an interference pattern can be observed. So in this application, the interferometer is used to process signals from an optical fibre sonar array. However, because it will be processing signals about how the sonar is measuring vibration, the interferometer itself needs to be isolated from vibration. So previous iterations of the interferometer had several susceptibilities to vibration, and this project aimed to address these. So the first susceptibility was the delay coil, which is 10 meters of extra fibre in one of the arms of the interferometer. In the previous iteration, the extra fibre was wrapped around a granite cylinder. However, due to deformation effects that occur when a cylinder is under dynamic load, this introduced too much noise into the measurement. So instead, several different delay coil designs were tested, and all of the designs were based on the idea of disrupting the uniformity of the delay coil. And in the end, the 3D printed spiral guide led to the cleanest measurement being made. The second susceptibility of the system was the way that the interferometer is mounted within the portable case. So these are the three different mounting styles that were tested, and they were all tested for their ability to isolate the interferometer from the vibration of the environment. So from this you can see that the shock mounts and the magnetic springs were comparable, however far less effective at isolating the interferometer compared to the specially designed vibration dampening foam, which performed incredibly well at both low and high frequencies. And the final susceptibility was the enclosure of the interferometer itself. So after investigation into acoustic isolation principles, a layered design was developed that would both block and dampen acoustic waves. So the outer layer would consist of acoustic dampening material, the inner layer would be acoustic blocking material, and the final inner layer of the interferometer enclosure would just consist of some vibration dampening material to add more mechanical isolation as well. So combining the solution to each of these susceptibilities, we get this result, which is a system which is much lighter, much smaller, and most importantly, does a better job of acoustically and mechanically isolating the interferometer from its environment.
Thank you, Madison. Please welcome Sabrina Wilson.
The laser is arguably the most important invention of the 20th century, and it only has 3 ingredients. The first is the gain medium, which is the atoms. The second is the laser cavity, which is the reflecting surface on either side. The higher the reflectivity, the stronger the cavity. The final ingredient is the pumping process, which is the means by which electrons in the gain medium are excited. So the physical process by which we go from just having three things to having a laser is stimulated emission. So unlike in spontaneous emission, where an electron transitions to a lower energy state because of random fluctuations in the electromagnetic field, stimulated emission is essentially photon FOMO. So an excited electron sees an incoming photon and it emits an identical one with the same energy, same frequency and the same direction. So DST has been developing a fibre optic sonar array which combines cutting-edge laser technology and sonar technology. How it works is that pressure waves, aka sound waves, coming from a submarine or a killer whale or even a snapping shrimp, change the length of the cavity, and changing the length of the cavity changes the frequency. However, the system can't distinguish between a change in frequency and a change in intensity, so in order to optimise the system, we need to suppress the changes in intensity in the laser. So the purpose of my project was to determine if the intensity noise in a laser could be predicted by a mathematical model which used spontaneous emission in the gain medium as the source of the noise. So what you're looking at here is a graph of the noise and the intensity of a laser versus the frequency at which the noise is changing. Each colour is a different pump power. The solid line is the data that I measured. The dashed line is spontaneous emission noise and the dotted line is pump noise. So you can see at low frequency, the laser noise is dominated by pump noise. However, at higher frequency, we get this resonance peak because the gain medium and the laser field are acting as a coupled linear oscillator, and that is the resonance between them. Now, any noise source can excite this resonance, but because the actual data is so much higher than the pump noise, this is strong evidence that the noise in a laser the intensity noise in the laser is being driven by spontaneous emission. So if we look at the same graph but for a much stronger laser, the results aren't so easy to interpret. Both the spontaneous emission noise and the pump noise are being drowned by what we believe to be thermal noise in the cavity. To give you an idea of how strong this laser is, the photon's bouncing between the gratings about 5,000 times before being ejected, which gives you a lot of heat building up in there. So hopefully in the future, with better thermal management, we'll be able to reduce that thermal noise in order to observe total suppression of that resonance peak, which not only would further validate the theory that spontaneous emission drives the intensity noise in a laser, which would be interesting in and of itself, it would have enormous practical implications for the performance of DST's sonar technology. Thank you.
Yeah, you can stay here. Thank you, Sabrina. Can I please now have the MD presenters to the stage?
Great presentations to everybody, so congratulations. To the presenter on the undersea, the underwater ducts and the shadow regions, is the inability of sound or sonar waves to be detected mutual between both ship and submarine? So is the ship as hidden to the submarine as the submarine to the ship?
I'm not actually sure on that one, sorry. Yeah. My apologies, I couldn't remember the answer.
And another question at the back.
Patrick, quick question. From all of the work that you've done with the displays, have you got any ideas how to incorporate that time data into like the polar graphs that you did?
What was that?
So yeah, in terms of incorporating the time data, so with the polar plot that you look at, it's actually updated continuously, so it's constantly evolving. And the other two plots just have that time history. So the advantage of having that polar plot is that you're always seeing the instant new data. So if something's just come into your field of, if something's just come in beyond your field of vision on the graph, then you'll know about it as it comes in, and then you can think, oh, well, I should look at that on the other two plots, because sometimes it's a little bit difficult to see what's going on the other ones if it's you've got a long time history and it's kind of a little bit small on the screen. Yeah.
Okay, and we've got a question from the other side of the room.
To Madison, I think it was, on the interferometer data, interferometer project. So as I understand, LIGO, the gravity measurement project, is the most sensitive Michelson infrarometer, and they'd have a lot of interesting tech on this sort of things. Do they use similar techniques to what you use, or did your project take any inspiration from their dampening techniques?
In short, no. They are definitely the same instrument. However, this is a optical fibre interferometer, whereas LIGO is a free space one. And the scale is just completely different. Yeah. So, in short, not really.
Thank you. And another question in the front.
A question for Patrick. So just on one, what were the tools that you actually used to build the user interface? And two, was this like simulated data coming in that you're feeding it to create this interface?
Yeah, so the GUI was made within the Qt framework. So yeah, mainly in the native QML language that comes with Qt, but also a little bit of C++ as well. And sorry, what was the second part of your question?
The data that was fed into this interface, was this just hard-coded, or you were feeding something that was simulated?
Yeah, the data is simulated, yeah.
And any further questions?
Yeah, I have a question for Vincent. How do you expect these acoustic tunnels to actually be used on like a maritime platform?
Short answer is I don't know. We're just seeing what these technologies can do, so that we can provide better advice on how to deal with them or how we could use them.
Quick answer on that. A theme for about 5 or 6 years now has been acoustic metamaterials and just what they might do on cloaking. So we're really just investigating what avenues they might be for, to start with point source frequency reduction, but just seeing what you can do with the technology.
And we had one more question at the front.
Yeah, this one's for Bryce. Just wondering what sort of neural networks, over here, what sort of neural networks you're looking at for the classification for your data?
So lots of the classification networks are actually pre-developed. There's software called Cloud Compare, which is specially developed for point clouds. Basically, that requires you to segment some sort of surface into different features, which is a benefit of using my algorithm because you actually get that built in. So then you can train your network on, a surface which is, say, rocks that are a certain distance off the surface. You can train on a sand bottom or a reef bottom. And yeah, that just opens up that possibility.
Thank you.
A question for Sabrina. So you suggested that it might be possible to suppress that excess thermal noise with better thermal management. Do you have any initial ideas on how you might go about doing that?
Yeah, I do actually. So how the optical fibre has a glass core and then outside like a plastic coating. So last week I went down to CES and I got like the plastic coating stripped off because plastic is actually surprisingly an awesome insulator of heat. Well, not like awesome, but like not, it could be way worse. So now that it's stripped and the glass is just bare, I'm going to try using like a heat sinking silicon type stuff and just like put the laser on that on like just a piece of granite. So hopefully, that'll just dump the heat out of the laser and it won't get trapped, in the cavity.
Okay, just wanted to make a couple of comments, and again on careers and things. The person I should call Dorothy after that question, or Dorothy Dixer, Dr. Scott Foster. Many of you won't be aware, we actually have a stream for our scientists that actually get to it. You become an S&T 7 as a principal scientist. You're actually an S&T 7 being recognised for being an outstanding scientist in your field, and Scott is one of the current 8, I think we have in the organisation. So that's just something else when you're looking at career paths through this organisation. The other thing I just wanted to reflect was you've actually got people from 4 different states standing up the front. So my apologies to the Melbourne team. They're about the only ones I hadn't made it to talk to during the time. But we've got 2 from Melbourne, 3 from Adelaide, Bryce from Sydney, who I saw just after he'd started, and the Sterling guys I saw last week. So again, that just reinforces DST as a global, an Australian-wide organisation. Global next week, Andrew. And team, thanks for the work you've done.